Now, what if I told you that perhaps Pythagoras didn't create this theorem and was, allegedly, a murderer? Yes, he may well have murdered people who tried to prove him wrong. Now, you want to know the story? It's a little bit later on in the video, but otherwise, hi guys and welcome to today's video on Introduction to Pythagoras Theorem, a continuation of some pretty awesome mathematics we've been dealing with lately. Now, this is going to show you where it came from, how it came to be, and a little bit about Pythagoras himself. I promise you I won't get too excited with the Pythagoras thing, but as is normal, ladies and gentlemen, by the end of the lesson above me, I want you to know what Pythagoras Theorem is. I want you to know how it came to be and determine if a triangle is right-angled. And whoops, a little bit of a spoiler alert, spoiler, that it has something to do with triangles, and know what Pythagorean triples are. Triple. Now look, we've been working with triangles for many, many years. I couldn't even tell you from when. Year 5, maybe year 4, probably from as soon as you could talk mathematically. And we know that for triangles there are all sorts of things we can do. We can find the areas, we can find perimeters of triangles using pretty basic formulae. We know there are different types of triangles. There are equilateral triangles, which are triangles with equal sides. There are isosceles triangles, where the sides are, two of them are the same, and there are scalene triangles, where all three sides are different. And one of the most exciting, the one we're going to be dealing with today, is right-angled triangles. Ladies and gentlemen, a right-angled triangle. Now, in the previous video, we knew that we could use the area of triangles to find volumes of prisms and all that type of stuff, but actually, we're going to use just one triangle. That's that right-angled triangle. And I think it's freaking awesome. Right-angled triangles are pretty much everywhere. They're the fundamental building blocks of all sorts of different stuff. And for bridges and all sorts of things mathematically, believe it or not, a triangle is the strongest shape known. Now, if you disagree with me, engineers out there, please do let me know. But as far as I understand it, triangulation is very, very important for structures. What do I mean by that? Well, if, for example, you were building a bookcase and you built it out of 4 pieces of wood, much like the diagram I've just said there, and you pushed it here, well, actually, believe it or not, the whole thing would just cave in on itself. If I was to put a triangular brace, a piece of wood that goes from corner to corner, and you tried to push it over, you would have a much, much harder job of collapsing that thing. That one triangle created quite a lot of support. Now, within there, you can see there are actually 2 right-angled triangles. And you're going to say, how do I know that's a right-angled triangle there, MaffsGuru? And I'm going to say, well, believe it or not, a right-angled triangle is a triangle what has a right angle in it. Yay! A right angle what is 90 degrees. So, that little sign there stands for a right angle, and it's 90 degrees. And because angles in a triangle add up to 180 degrees, we know that this angle here and this angle here must then also add up to 90 degrees. So angle 1 plus angle 2 must also equal 90 degrees. Now, right angle triangle is freaking awesome. And for right angle triangles, we can work out areas. We can work out perimeters, which is the length all the way around the edge. We can use trigonometry. Now, trigonometry, I hear you say, what is this trigonometry stuff? Well, if you haven't met it yet, it's an awesome subject that I love teaching. And a highlight, silly old Harry caught a herring trawling off America. And you're going to say, what? Has he lost it? What's gone wrong? Well, just chill. Silly old Harry caught a herring trawling off America actually has some sort of sense. But we're going to deal with this Pythagoras Theorem. Again, if you were to say to your parents, much like I said last time, about trigonometry or Pythagoras, they would run screaming. Yeah, screaming from the room. Because in those days it was actually quite difficult to work out, but not in your little age, because you got triangles, you got calculators and the such. So the way we know it's a right angle triangle, as I say here, is it has this 90-degree angle in it, and right angle triangles must, I might even say, be labeled with a right angle. Otherwise, you shouldn't necessarily be able to know straight away it's a right angle triangle. Now, I was always taught at school that calling people names was a bad thing. Yes, so if I walk up to someone now and say, "Oi, big head," apparently that's not a good thing to do. Saying someone has a big head is actually quite unfair. Please don't say I have a big head. It's really hurtful. But triangles actually have names. We've already called them isosceles, equilateral, scalene, but so does the side lengths. Now, the one I'm most interested in at this moment in time, and here is my right angle triangle, is actually the name of this side here. The slopey side, or the slanty side if you wish, has a special name, and that's called the hippopotamus. No, I'm just joking. It's not the hippopotamus at all. It's the hypotenuse. Hypotenuse. The hypotenuse. Now, mathematicians, I'm afraid, are absolutely lazy. And as a result, we would spend all of our day in bed. No, that's not what I mean. We would like to very much make these things shorter. So we don't like writing hypotenuse. We will either abbreviate that to the word hype, or sometimes even H in a circle. I vary depending on what the question is, but the longest side is actually the most important one. And lots of people strangely get confused with the longest side. If the triangle is drawn this way, then it's actually really easy to see where the slanty side is. But what if I drew my triangle like that, for example, and did my right angle there? Which side is slopey? Well, you could argue there's a slopey side and there's a slopey side. Why? Because they are sides what slope. But, ladies and gentlemen, I use a little bit of a trick. I actually think of the right angle as an arrowhead. There is an arrow pointing to my hypotenuse. So in this situation, if I was to draw a line there, there is my arrow. So this one here is my hypotenuse. Now, do you wake up in the morning and ask yourself, how, MaffsGuru, did they build those pyramids? And I would say to you, I don't know. Why did you wake me up at 3 in the morning to ask me about pyramids? Just Google it. And so, lo and behold, ladies and gentlemen, I went away and Googled it. And I don't think the consensus is no one really knows. It's very clever how they did it. But I've got a feeling it had something to do with triangles. Now, what they did have in ancient Egypt in lots of different ways, I think, was the general idea of squares. They were pretty good at making squares. So, a square here, I'm going to put these little lines in of 4 by 4 by 4 by 4. So, there is one square. And I've got another square here, slightly bigger, which I'm going to say is 5 by 5 by 5, and a slightly smaller square, which is 3 by 3 by 3 by 3. Now, interestingly, if you take those 3 squares and join them together in a particular way, this is what you actually end up with. There is one square, so I'm going to say that's my 4 by 4 by 4 by 4. Here is another square here. Now, I'm not drawing these to scale, by the way. 3, 3, 3, and 3. And actually, if I was to put the other square here, which is the 5 by 5 by 5 by 5. If you put those 3 squares together, they will form a beautiful right angle triangle. Now, that does not mean you can run out and grab every square in the world and make a right angle triangle. Interestingly, it was only specific to 3, 4, and 5. Oh, hold on a moment. 3, 4, 5. That's going to come in important in a moment. It was only works with a perfect right angle if I had a square of 3 by 3 by 3, 4 by 4 by 4, and 5 by 5 by 5. Now, someone, and we will say Pythagoras at this moment in time, looked at the areas of each of these squares, and he went, well, I wonder what the area is of this square here. And if you remember, the area of a square is find a corner and multiply it together, then the area of this worked out to be 9 square units. What about with the area of this? Well, 4 by 4 by 4 by 4, or a square of 4 by 4, gave me an area of 16 square units. And this one here, which was 5 by 5, gave me 25 square units. Now, what do you notice about 16 plus 9? Nope, hold on. You got it, didn't you? It was 25. So what Pythagoras, or someone, will come back to it in a moment, seemingly discovered that certain squares, when put together, if you could add the areas of the 2 smaller squares together, and you could get the area of the larger square, then you got a right angle triangle. And it was like, this was mind-blowing. So 9 plus 16 gave me 25. Yes? See that? Now, that triangle there is actually fairly special to us. It's called a 3, 4, 5 triangle. And I'll come back to explain that in a moment. But the question is, are there other triangles this can actually happen with? Well, actually, it turns out there are. If you take a square with side length 5, another square with side length 12, and let's put these little marks in to make it mathematically correct, and another square of side length 13, they, interestingly, also fit together. So there's my 5, there's my 12, and there's my 13. That doesn't look like a square at all, MaffsGuru, so why don't we just... No, that doesn't look anything like a square either. We'll try it one more time before we give up. There we go. Now, if I put those together with 5, 12, and 13, let's look at the areas of each of those. Well, the area of this is 5 times 5, which is 25 square units. I'm just going to put 25 for the moment. 12 times 12 is 144. And I happen to know, using my calculator or just remembering it, that 13 times 13 is 169. So for this to create a right angle triangle, this plus this must equal that. And they do. So excited. And funnily enough, one of these triangles here, this 5, 12, 13 triangle, is also an important triangle. Now, what do you notice about this slanty side, this hypotenuse? Well, this is always the largest side. So the hypotenuse of a right angle triangle is always the largest side. And that's also coming to be really, really important. Now, Pythagoras Theorem. It's called Pythagoras Theorem, so he must have invented it, mustn't he? He must have done all of that hard work before. Well, let me just load up a little bit of a website here. This comes from a website called gizmodo.com, and I use this little story all the time. And it says, was Pythagoras really a murderer? Now, obviously, there's a lot of allegeds here, but the interesting thing about Pythag was he was an incredibly intelligent guy, and he was a bit of a maths nerd. But he was a little bit fanatical about it, to the point that, whether you know it or not, he actually started a religion called Pythagoreanism. Now, I don't know about you guys, I tend not to go to church on a Sunday. Well, I certainly haven't gone to a church of Pythag at any time soon, because that would be a little bit maths geeky. But he started this religion, and he started to attract lots of other very intelligent people, younger people. And he allegedly may well have got all of these people to work really hard in lessons, much like as I do as a teacher, and then he stole all of their ideas. Or, allegedly, he borrowed them and published them under his own name, which probably isn't stealing at all, really, much. Now, he ended up knowing, as I scroll down, that he decided that every single number in the world could be expressed as a fraction. Every number, everything in the world can be expressed as a fraction. Doesn't matter what it was, it could always be a fraction. And we now know that that's not strictly speaking true. But at the time, when maths was new and exciting and no one had the cash calculator, everyone just believed him. It was like, well, all right, fair enough. You seem to make sense. You're a bit weird. You're a bit geeky. Yep, we'll just say yes and hopefully you'll go away. Until, sadly, a guy came along called Hippasus. Now, it's strange, that sounds like hippopotamus or hippocampus or hypothalamus or any other part of the body, but Hippasus basically realized that Pythagoras was wrong for something. And he found it by working on a triangle here with different sides. And he basically said, Pythagoras, you're a bit of a nutter. You're wrong, dude. You're so wrong. Now, obviously, for anybody who starts a religion, to be told they're wrong, not necessarily a great thing. But if you were going to tell someone you were wrong, you'd probably choose the best place to do it, wouldn't you? I mean, the last place you would choose to do it would be on a boat. Yeah, and unfortunately, Hippasus may well have been clever, but he wasn't that clever, because, allegedly, whilst on this boat, Hippasus turned around and went, "Yo, Pythag, mate, I think you're wrong." Now, Pythag sort of went, by the way, I'm making all this up. I wasn't on the boat. I've got no idea if I was that old. Anyway, me, wrong, I'm not wrong. And he went, yeah, you were, mate, you were wrong. I've proved that for this triangle thing, it can't be expressed as a fraction. Well, the thing was, Hippasus was perhaps the only person on the boat who actually wasn't loyal to Pythagoras. And so it is alleged that some of his supporters may well have, thrown him over the boat. Really? On a boat? Me? I'd have probably done that on dry land, with a huge distance between me. I'd have sent him an email. See what I did there? There was no email. No one really knows whether Pythagoras actually created this rule or not, or whether it was one of his students, but who cares? The point of it is, we actually came up with this idea, or someone came up with this idea about the areas of squares, that for certain squares, when we add the two smaller squares together, or the areas together, they gave us the area of the bigger square. Now that's a really long way to say something, and so we came up with a shorter way. And what we said was, if we have a triangle here, which is right angled, and we called that A, and that B, and that C, then the area of a square here would be expressed as A squared, because to find the area of a square, you take the side times the side. The area of this square here, would obviously be B squared. And that would give the area of this square here to be C squared. And what we've said is the area of this square, A squared, added to the area of this square must be equal to the area of the larger square. And ladies and gentlemen, that's where Pythagoras' theorem came from. This here is called Pythagoras' theorem. Now, we don't generally write it as A squared plus B squared equals C squared. We write it as C squared equals A squared plus B squared. And interestingly, yes, I teach in Australia, but with a very British accent, and in the United Kingdom, I think we do it a little bit more sensibly by saying that A squared is equal to B squared plus C squared, because A, B, C, easy as 1, 2, 3, you know. Anyway, had a bit of a Michael moment going on there. But the point of it is, it doesn't actually matter what letter you choose here. If I was to do my triangle with X, Y, and P, for example, what I have to remember is the longest side is always the one that's on its own. So in that situation, P squared would be X squared plus Y squared. And lots of people say to me, well, does it matter whether I put X squared plus Y squared, or could I have written P squared equals Y squared plus X squared? And I'll say to you, absolutely, I should, Coco, because if you think about it, 2 plus 3 is 5, and 3 plus 2 is 5. The order I do addition, whether it's a single number or square numbers or whatever else, actually makes no difference. So, with that in mind, I move on to my idea of Pythagorean triples. Now, actually, we've already met them, because earlier I talked about triangle called the 3, 4, 5 triangle, and a 5, 12, 13 triangle. They are two examples of Pythagorean triples. I believe there's another one, which is a 9, 40, and 41. These are all Pythagorean triples. What is a Pythagorean triple? It is a right-angled triangle that has whole number side lengths. Whoop, whoop. And there are lots of them. And you're going to say, really? Do I have to remember all of them? Well, no. My advice to you is for triangle 1 and 2, remember these. They turn up in questions all the time. But ask yourself the question here. Is a 6, 8, 10 triangle A, right-angled, and B, Pythagorean? Well, actually, the reason I've drawn it underneath that triangle there just happens to be because if you look at how have I gone from 3 to 6, from 4 to 8, and from 5 to 10, I have doubled the sides. Now, if the sides have all doubled, then that triangle will still be right angle. And so, yes, 6, 8, 10 will also be a Pythagorean triple. And so will 4, 12, and 15. Where did I get the 4, 12, 15 from? Well, I took my 3, 4, 5 triangle and multiplied it by, no, not 4. Let's try that one again. 9, 12, 15, because what I did was multiply everything by 3. All good? So we can now use that information to try and decide whether a triangle is right-angled or not. So let's take this triangle here. Let's say 4, 6, and 12. Is this a right-angled triangle? Well, the way we're going to test it is we know that for it to be a right-angled triangle, it has to follow Pythagoras' rule. So we have to know that a squared is equal to b squared plus c squared. I did the English one, I know. Messing with your head, isn't it? All right, so a squared is the one that has to be the hypotenuse. So it's got to be the slanted. Let's call that b, and let's call that c. Now, you're going to say, does it matter? And I'm going to say b and c make no difference at all. For it to be a right-angled triangle, we need to know then that 12 squared is equal to 4 squared plus 6 squared. Well, 12 squared I know is 144 because 12 squared is 12 times 12. 4 squared I know is 16 and 6 squared is 36. Now, before I go too much further, there is no way that 16 plus 36 is going to give me 144. So using that simple test, I can say, therefore, this is not a right-angled triangle. Well, ladies and gentlemen, I hate to tell you this, but I have had a blast doing that lesson. That was awesome. I need to do a bit more role play. I've got to get some costumes. I've got to get dressed up as old people. Don't go there. I know I'm already old. Introduction to Pythagoras Theorem, and we are done. Thank you so much for watching. Hopefully it was interesting and useful for you. The next video will actually find missing side lengths and use Pythagoras Theorem in a slightly more interesting way. But, do you know what? It's been good seeing you today. Have you subscribed? No? Click the button there for me if you would. And if not, oh, come on, dude. I need the support. Get out there. Please tell your friends that I exist. Tell them. Send them the link. MaffsGuru.com website. YouTube.com/MaffsGuru. I am there. If not, there's a video loading over there for you to watch. Have a good evening. Have a good day. I'll see you next time.